Okay. So in the last lecture, we talked about a proof for the binomial distribution, right? And one proof was that basically, like the intuitive proof. So let's write down the binomial distribution. So basically, if probability of success is P, right? So whenever you think of probability of success, think of the experiment where we roll a die, and the success, for example, is defined as getting a 6. So in that case, probability of success is 1 divided by 6, right? So probability of success is P. Trials are random. Trials are independent. And finally, and there are n trials in total, right? So basically the keyword is that they are independent from each other, right? When we roll the die n times, the outcome doesn't impact the other trial. And we are doing this experiment n times, right? So probability of succeeding x times, right? And note that in the binomial distribution, we write x as succeeding x times because x is usually what we vary. X is defined as the random variable, right? So x can be x can be 0 all the way to n, right? So we can succeed 0 times, once, or all the way to n times, right? So we said that this is the binomial distribution, and probability of x is n choose x times p to the power x times 1 minus p to the power n minus x, right? That's the binomial distribution, right? So basically, intuitively, since the sum of probabilities must be 1, right? So if we repeat this experiment n times, and x can only take these values, then by the axiom of probability, sigma p to the power x times 1 minus p to the power n minus x for x equal to 0 to n, this must be 1, right? And this is according to the axiom of the probability. According to axiom of probability, right? That was one of the axioms, that the sum of probabilities is 1. Okay? But another proof is the algebraic proof, right? And that comes from the algebraic proof comes from that comes from the binomial theorem, right? The binomial theorem tells us that a plus b to the power n is equal to a to the power, or maybe let's write it this way. N choose 0, then a to the power n, b to the power 0, plus n choose 1, a to the power n minus 1, b to the power 1, plus dot, 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 plus n choose n, a to the power 0, b to the power n, right? This is from algebra, right? So you, like this, the familiar case of this that you have seen for sure is a plus b to the power 2 is a squared plus 2ab plus b squared, right? Or a plus b to the power 3 is a cubed plus 3a squared b plus 3ab squared plus b cubed, right? So this was also, you remember the Pascal triangle, right? 1, 1, 1, 1, 2, 2, 1, and so forth, right? These numbers in the Pascal triangle, they come from the binomial. Basically, these are these coefficients, right? These are these numbers in the Pascal triangle. So basically all we want to do now is to prove that this equality holds. We want to prove this, but we don't want to use the axiom of probability. We want to, we want to algebraically show that this is correct. So any ideas how we can do that, knowing this equation? So knowing this equation that I put in a box, we want to show that this sum is equal to 1. So it's, I will show you the proof because it's not really part of our course, right? So basically it's a trick. All we do is that in this equation is correct for any A and any B, right? So what we will do is we will put A equal to P and B equal to 1 minus P, right? So that equation is correct for any A and B. It's a general equation, right? So what I do is that I put P and 1 minus P, right? And what happens is that the left-hand side becomes 1, right? Because it becomes P plus 1 minus P to the power n, right? And the right-hand side becomes 0 from n, a to the power p, a to the power n, that's p to the power n times 1 minus p to the power 0 plus n choose 1, p to the power n minus 1, 1 minus p to the power 1 plus ... right? And the right-hand side is exactly the right-hand side of the, basically it's exactly this equation. And the left-hand side, that's 1, because P and P cancel out. Right? So this is not really a part of this course, right? If you didn't understand it, no worries. I just wanted to show you why, why this is called binomial distribution, because the equation for binomial distribution, this probability equation that is in the box, is exactly the same as the binomial theorem, right? And this is the binomial theorem, right, up here. Any questions? All right, so let's look at, we saw these combinations of 3 out of 10, combinations of 10 out of 15 and so forth, but let's look at the numbers that they give us, right? To get a better feeling. For example, 10 choose 3 is 120, 15 choose 10 is 3,000, and 100 choose 4, it's a large number, 3 million, right? So if you have, for example, 100 people, such as this class, there are, close to 4 million ways that we can form groups of size 4, right? I'm sure many of you thought that that number is lower than that, right? You didn't really think that there is 4 million ways that we can create different groups of size 4 from this class. So let's look at an example. Each sample of water has a 10% chance of containing pollutants. Assume that samples are independent, right? So you do want to basically look for this in the questions, right? They have to be independent, otherwise we can't use binomial distribution. the probability that in the next 18 samples, exactly 2 have pollutants, right? So basically, the question is telling us that we are selecting 18 samples, so n is equal to 18. And we want to have 2 pollutants, so this is x. And there is a 10% chance of success, right? So in this question, success is defined as having pollutants, right? So this is P. So that's it. All you have to do is to find basically these 3, these 2 parameters, n and p, and the random variable x. So the solution is here, right? We say it's 18 choose 2 times prob p to the power 2 times 1 minus p to the power 18 minus 2. So this 16 is actually 18 minus 2, right? So for example, if the question said probability that in the next 18 samples, exactly 2 don't have pollutants. Right? Then there are 2 ways we can solve this question, right? One way is that we can change the definition of success. So we define success as not having pollutants, right? Then in this case, probability of success will be 0.9, right? Because there is 10% chance of having pollutant, it means that there's 90% chance of not having pollutant, right? So for this, probability of x equal to 2 will be again 18 choose 2, and then 0.9 to the power 2, 0.1 to the power 16, right? That's the solution. There's another way we can solve it. I let you think about it at home, but it's basically the same answer. Yep.
You said it's 16 hot pollutants, or?
Exactly. Yeah, that's the solution. Yeah. So the other solution would be the other basically approach. So we want to solve this other question that 2 don't have pollutants. So we change the question and we say 2 don't having pollutants. That means that that's equal to 16 having pollutants. What's your name?
Oliver.
Say it again.
Oliver.
Oliver? Yeah. And you get the same answer. So with 16 having pollutants, P doesn't change. Success is still defined as having pollutants, so P is still 0.1. You don't change P. Right? And the answer that you get is exactly the same answer that we got here. So this is the answer. Any questions? I have actually one more request for you guys. So keep an eye on that red button up there that shows that it's actually being recorded right now. So we are good, right? So I may forget, but if it didn't crash in my experiments, but if it does crash, check for that, red button at the top. All right. So the next question, we want to answer basically the same question, but here we want to have at most 3 samples, right? So that means that we either want to have 0 samples that have pollutants, 1, 2, or 3, right? So it's quite simple, right? In the equation for the binomial, we plug in x as 0, 1, 2, and 3, and that's it. We add them up. Any questions? Okay. So since the answer is not here, I just write it down quickly. So this one will be 0 out of 18 times p. P is 0.1. P to the power 0, and then 0.9, which is 1 minus p to the power 18. Just check if there's 18 samples in total. Yeah, 18. So that's the first term plus 18, choose 1, and then 0.1 to the power 1, 0.9 to the power 17, plus the other two terms. Okay. So the next question is asking us what's the probability that we have at least 3 samples that contain pollutants, right? So we can answer this one similar to before. We can say, sorry, at least 4. So we can say we can either have 4 or 5 or all the way to 18. Right? What's another way? This is so many terms, right? This is like 14, 15 terms. 15 terms, I guess. So is there an easier way we can solve this? Instead of 15 terms with fewer terms? Yeah?
You do the probability of x is less than or equal to 3, so you do 1 minus probability x is less than or equal to 3.
Yeah, exactly. We can look at the complement, right? Yeah, what's your name?
Cordell.
Cordell? Yeah, that's correct. So basically what we can do is that the easier solution is we can say, you have seen this a lot in the sample questions, right? When some probabilities are, involving a lot of different terms, it's sometimes easier to look at the complement, right? So we can write it as 1 minus p of x less than 4, right? And that only has 4 terms, right? So x can vary from 0 to 3. That's only 4 terms. Any questions? Okay. All right. We can also calculate probabilities for x being in a range, right? So here we want to calculate probability that x is more than or equal to 3 and less than 7, right? So again, it's super easy. All we do is that we set the bounds of the summation from 3 to 7, right? Because it starts from 3 and it has to be less than 7, so that's 6. Any questions? Okay. So one very important equation in fact, 2 important equations for binomial distribution are the mean and the variance, right? So the mean is NP, and the variance is NP times 1 minus P. Again, these equations are in the crib sheet. You don't need to memorize them, but it's very important to know what they mean, right? So basically, like if we consider our running example of rolling a die, right? In that example, P is 1 divided by 6, right? And let's say we roll the die 30 times, right? And we define, so here when we said P is 1 over 6, we basically defined success as getting a 6, right? Or any other number, it doesn't matter. Can be defined as getting a 1, right? Because for all of them, probability of success is 1 divided by 6. right? So in this case, the expected value is going to be NP, which is 30 times 1 divided by 6, and that's 5, right? Right? And that should make sense to you, because if we roll the die 30 times, in average, we are expected to get 5 6s, right? And that's the meaning of expected value. It means in average, you know, how many times do you expect to succeed? Right? So, for example, in the previous example that we had with the pollutants, right? Where is it? Here, right? Oh, where is the question? So here the probability of success is 0.1, and we have 18 samples. So expected value of x, which is mu, is going to be NP, which is 18 times 0.1, and that's 1.8, right? Right. So that means that if we have 18 samples, in average we expect to have 1.8 samples that contain pollutants, right? And again, similar to the experiment of rolling a die, the average number that we get is 3.5. Again, here the number is fractional, right? So it's impossible to have 1.8 samples that have pollutants, right? Because the number is integer, must be integer, right? We either have 1 or 2 or 3 or some other number, right? So probability of having 1.8 samples is 0, right? This number means in average, how many samples do you expect to have pollutants, right? Any questions? Okay. Okay. And in the next few slides, I provide some intuition into variance, right? But for now, just accept that this is the equation of the variance. This is not hard to prove. We won't prove it, but instead I show some some intuition into this number. Okay. So the first distribution that we saw was uniform, which is a very simple distribution, right? It means all probabilities are equal, right? The second one that we saw was binomial, right? So in binomial distribution, we have a fixed number of trials, and we want to have X number of successes, right? The next distribution that we cover in this chapter is called geometric distribution, right? And here, the number of trials that we do is X. We don't know how many trials we are going to do, right? The number of trials is not set anymore. And we basically continue until we succeed. Right? So here what's going on in the geometric distribution is that this is for trial 1, this is trial 2, this is trial 3, and this is trial X. We are doing X trials, right? And all of these are failures, failures, and then the X one is a success, right? So that's how the geometric distribution is set up, right? Once we succeed, we stop the experiment, right? Because we only wanted one success. So basically, since these are the similar thing between these distributions is that both of them are, actually I don't mention it here, but both of them must be independent, right? So these X trials here are independent from each other, right? So since they are independent, we can simply multiply the probabilities, right? So probability of failure in the first example is 1 minus P. Probability of failure in the second example, second trial is 1 minus P, and a bunch of 1 minus P's. So a bunch of 1 minus p's are multiplied. And then for the last one, we have a success. Probability of success is p, right? And what I wrote here is exactly this. We have 1p, and we have all of these. The number of these is x minus 1. And 1 minus p time to the power x minus 1. Right? So the proof is really, really simple. In fact, you don't really need the equation. The proof is even simpler than binomial distribution. So let me give you, there's one example, but I just thought of an example that I think is much easier, right? So here, roll a die until you get, so since we always say 6, let's here just put a different number, a 5, right? So 5 is defined as success, right? So we keep rolling the die until we get a 5. Right? So let's say you're playing a game, and in order to win the game, you need a 5, right? So let the number of times that you roll the die be x, right? So the number of times that you roll the die is, we call it x, right? So we are rolling the die until we get a 5, and what is probability of x equal to, I don't know, 10, right? So we want to find out what's the probability that we need to roll the die 10 times to get a 5. Right? So the first solution is we use the geometric distribution. The answer is p to the power 1 times 1 minus p to the power x minus 1. And p is 1 over 6. And 1 minus p is 5 over 6 to the power 9. That's the answer. So the second solution is not using the equation at all, right? So we want to roll the die 10 times to get a 5, right? So that means that 1, 2, 3, 9, and 10. Right? So I denote 5 as success, and anything other than 5, so I call this 5 prime. It's an abuse of notation, but we call anything other than 5 as a failure, right? So I want my first experiment to be a failure, my second roll to be a failure, third to be a failure, ninth to be a failure, and I want the 10th one to be a success, right? Because the question said, keep rolling the die until you get a 5, right? So it means that in none of the previous trials, right, in none of these guys, I got a 5. Otherwise, I would have stopped the experiment, right? And probability of failure in the first trial is 5 divided by 6. In the second trial is 5 divided by 6. ... In the 9th one is also 5 divided by 6. And in the last one, probability of success is 1 divided by 6. And that's the answer. Right? Any questions? So this is, in fact, quite similar to the binomial distribution, right? So the question, like a similar question to this one that we can look at, which is the answer is binomial, would be the one that I write up here. So roll a die 10 times, success is getting a 5, right? So again, we define the success as the same thing. You want to get a 5. What is probability of succeeding once, right? So here I roll the die 10 times. Again, I define success as the same thing. I want to know what's the probability of succeeding once, right? So this is not a geometric distribution, right? And the answer is different. So here the answer was this for the geometric distribution. Here the new answer is going to be 10 choose 1 times 1 divided by 6 to the power 1 times 5 divided by 6 to the power 9. So this is the answer here, right? And you see they are very different. In fact, this one is 10 times bigger because this number is 10. 10 choose 1 is 10. Right? So the binomial probability is 10 times bigger than the geometric probability. Right? And the reason for that is that for the binomial basically experiments, all of these are acceptable. So this is experiment 1, 2, 3, 10. I can have a success in the first trial and then failure in all of the other ones. I can have a success. I can have a success in the second trial and failure everywhere else, right? So this is binomial. But in the geometric case, the only answer is I fail, 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 and then I succeed. Right? So that's the key difference between geometric and binomial, right? So in binomial, my success can happen anywhere. It can happen in the first trial, second trial, all the way to the 10th trial, right? But in geometric, the experiment is different. In geometric, I stop the experiment once I see a success, right? So it means that the success always happens in the last experiment, right? And because of that, the geometric probability is always lower than the binomial, or it's equal to. Any questions? Okay. All right. So let's look at another example. The probability that a wafer contains a large particle of contamination is 0.01. Assume that the wafers are independent. What's the probability that exactly 125 wafers need to be analyzed before the first particle is detected, right? So again, let's say we want to analyze the particles that have, some failure. So we will stop testing them until we find the first wafer that has some contamination, right? And we want to calculate the probability that 1 to 124. So I have a failure in the first trial, failure in the second one, failure in the 124th one, and a success in the 125th one. Right? So we use the geometric distribution and the probability is quite low. Any questions? Okay, so again, for geometric distribution, the equations for the mean and variance are very important. The mean is 1 over p, and variance is 1 over p divided by p squared. Right? So again, the mean is quite intuitive, right? And the reason for that is even without telling you this experiment, you know the mean by your heart, right? So let me tell you why. So again, let's go back to our running example. So we roll a die until we get a 6, right? So this time we want to get a 6. In average, how many times should we roll, right? So the goal is we want to get a 6, right? So we keep rolling the die until we get a 6. So we might be lucky and we roll a 6 in the first trial, or we might be unlucky and roll, you know, 1,000,000 times and not get a 6, right? But in average, how many times should we roll the die to get a 6? 6 times, right? So the answer, as you knew by your intuition, is 6 times. And we can use the equation. The expected value or mean is 1 over p is 1 over 1 over 6, because the chance of getting a 6 is 1 over 6, and that's 6. Any questions? Okay. So let's look at another example. The probability that a bit has error is 0.1. Assume that transmissions are independent. Let the random variable x be the number of transmissions until we see the first error. Find the mean and standard deviation of x, right? So p is 1 over 10, so mean is going to be 10. And we plug into the variance, and the variance that we get is 90, right? So we will talk about this later on, but standard deviation is defined as the square root of the variance, or sigma, right? So we will talk about it a lot later on. So sigma will be square root of 90, or 9.5. Any questions? Yep.
Can you explain just the difference between the definition of the standard? I know that there's a difference in this having one is the square of the other, but I want to know the meaning.
Yeah. Yeah, that's a very good question. I don't know if I should explain now or leave it to the later chapters, because in the subsequent chapters 5 and 6 we talk about standard deviation a lot, right? But one example I can tell you is that standard deviation is what so if we look at the height of the students in this class, right? We have a mean of the heights, let's say 170 centimeters, right? And we have a standard deviation, right? So a standard deviation would be like, let's say 5 centimeters, right? So it means that many of the people in this class are between 170 plus minus 5 centimeters, right? But variance will be standard deviation to the power of 2, right? So it will be 25 cubic centimeter, square centimeter, right? So it's not something that we really intuitively, it's a different dimension, right? So what you have in your mind as, like a variation of the data, that's standard deviation. That's not variance. Variance is the square of standard deviation, right? So perhaps we should have defined standard deviation first and then defined variance as the square of that. Okay? That's a more intuitive way. And we see that a lot later on, like there is a concept that we introduce, it's called confidence interval, right? So like when you buy something and look at the weight, it says 40 grams plus minus 1, right? So that one gram is related to the standard deviation. Other questions? Okay. Okay. All right. So before we move forward with more distributions, right? So the rest of this chapter is we define other distributions, right? let's see if you can name two distributions, F1 and F2, right? F1 and F2 that have the same mean. So the mean of these distributions are 8, but the variances are different, right? So can you define an experiment where the mean is 8, but it has a 0 variance? Let's start from the top one. Yep.
You might be wrong, but maybe geometrical, since there's only one success.
Say it again.
Maybe geometrical, because there's only one success, and the binomial has success,
Yeah, okay. So I see how you think. But in geometric distribution, that's a good way of thinking. But in geometric distribution, x varies, right? So x can be 0, x can be 1, x can be, all the way to infinity, right? So the variance is not really 0, right? So when variance is 0, it's not really a probabilistic or stochastic event anymore, right? It means that there's no variance, right? So, let's say you roll a die, but all of the numbers on the die are, for example, 1, right? So that's, that experiment doesn't have any variance because you always get 1, right? Or like how many of you remember that scene from the Dark Knight movie when Robin flips a coin, right? So both of the sides are head, right? So assume that both sides of a coin have number 8 on it, right? So you define the experiment as flipping that coin, right? So in that experiment, the variance is 0 because there's no variation. You always get an 8. And both sides of the coin have the number 8 on them, right? So the expected value of the number that you get is 8, right? So can you basically propose another experiment where the expected value is 8, but the variance this time is non-zero? And you have freedom to define the experiment, as you want. It can be like flipping a coin or rolling a die or anything, like pulling a card out of a deck. So someone from the third row from here. So it's 1, 2, 3, 4, and 5 candidates only. So one of you 5 guys, can you think of one experiment where the expected value is 8 and the variance is non-zero? Yeah, go ahead.
If we combine two vector problems, 53 and 53, and I think we have a total of 8 aces.
Okay.
Can you example?
Say it again from the beginning.
Two decks of cards.
Okay.
And with both combination we'll have 8 aces.
Okay.
And would that be an example for that?
8 aces. And what is the random variable? Is the non-random variable the number that's on the card? Because the number on ace is 1, right? So the expected value, what would be? Is the deck a complete deck or is only aces?
It's 2 decks, which is
2 decks, okay.
53 plus 53. That's the total number.
52, I think it's 52, right? Each deck?
Exactly. Number
52.
Okay. So 104 in total.
Yeah.
And 8 of them will be aces.
Okay. But the expected value of that, I'm not sure if it's 8 because the numbers on cards are 1, 2, 3, all the way to 10, and then you have jack, 10, like king, queen. What do you define those when you calculate the expected value? Like what is the value of jack when you calculate the expected value? Do you define it as 11 or? And I'm sure the expected value won't be 8. I need a much simpler answer, right? So construct a very simple experiment. So someone from the row right below that one. So the fourth row. So you guys. No. Sorry, I want somebody from that row. So 1, 2, fourth row from here. So I help you out a little bit. It can be a coin, right? So the example can be as simple as flipping a coin, right? So when we have a coin and flip the coin, if both numbers on the coin say 8, then the variance is 0, right? Because there's no variation. We always get an 8, right? But what numbers can be on the coin such that the average number that we get is 8? Maybe one of them a little less than 8, the other one a little more than 8, such that when they average, we get an 8, right? You wanted to answer? Yeah.
My answer was going to be that you want to buy something, and the prices are $6, $7, $8, $9, $10 in different stores, and the average is $8, and the variance is not 0.
Exactly, yeah. That's correct. What's your name?
Nikolai.
Nikolai? Yeah, that's correct. So for example, you're buying something, right? And the price of that thing, let's make it a bit easier, right? So the price of that thing that you're buying is either, let's say some stock, right? And it fluctuates between 7, 8, and 9, right? It only takes 3 values, 7, 8, and 9, and the probability of them are equal, right? So with the probability of 1/3 is 7, with probability of 1/3 is 8, and with probability of 1/3 is 9, right? So in average, we are going to, get an 8, pay $8 for that, right? And the variance is non-zero. Or the coin example that I was saying, I'm sure you thought of this. I don't know why you didn't answer. So the coin would be has 2 numbers, 7 and 9, right? So we flip a coin here. One side of the coin has 7, the other side of the coin has 9, right? So in average, we get an 8, right? Because 7 has a probability of half, 9 has a probability of half, and when we do the equation for expected value, we get 8. Right? And the variance is non-zero, right? Variance of non-zero means that we have variations, right? We don't get the same answer. Yeah?
So why is it the values? Shouldn't it be a mean, a probability? Because the other example we had, you roll a die, so it's 1/6.
Yeah?
Shouldn't the example be a race with 8 cards and then 1/8, so it's 1/8, with a mean of 8?
I'm not sure. So can you say the example again? So is this our aim? We want to come up with an experiment which has an average of 8 and non-zero variance?
Well, the average should be the probability, no?
No, so that's a very good question, right? So average is, so look here, that's a very, very good question. It's E of x, right? Look at this thing here. This is x, right? It means that what's the expected value of x, the random variable? It's not probability, right? So if you remember the example of rolling a die, so if we roll a die, then expected value of x is 3.5, right? The number that we get in average is 3.5, right? And this number, 3.5, is the average of the numbers that show up on the die when we roll it. It's not probability.
Right? What was the example on the previous slide? The 6.
Sorry, this is the first slide. Do you mean this one?
No, we had a slide before this, and you gave the example for advice, and it was 6. The mean was 6.
Oh, yeah. So basically in that example, so that one was we roll a die until we get 6, right? So are you referring to this one? We roll a die until we get 6. What's the expected value of the numbers that we have to roll the die? Is this the example you're referring to?
I think so.
Yeah. So we roll a die, let's say x times, right? Because we don't know how many times we are rolling. Until we get a 6, what is expected value of x, right? And the answer is 6, right? Because it's 1 over p, right?
Okay.
Yeah.
So this case isn't even geometric, but the second.
Yeah, so no, these examples that I'm referring to are much simpler. They are more intuitive examples. They are not binomial or geometric. They are general, So, like here, like in geometric or binomial, I'm flipping a coin, n times, or I'm rolling a die, n times. These are much, much simpler sort of thought experiments, right? Where I want to find an experiment where, the average outcome is 8, and it has a variance of 0, right? This is much more, fundamental than binomial and those distributions. Right? So let's show a few, PDFs, right? Probability distribution functions. So for the first one, probability of getting an 8 is 1, right? Because the sum of probabilities must be 1. Yeah. Yep. Yeah, yeah.
The formula is the mean equals to E of X, and then is 1 over P. So
Yeah.
Y is the expected value of 8 is the average of 7 and 9. And probability of getting 7 is 1 over 2. Probability of getting 9 is 1 over 2. Then that's 1 over 2 times 1 over 2.
No. Yeah, that's a good question. So let's look at basically this case, right? So I think this was one of the first example that we mentioned about expected value. So we flip a coin with numbers 7 and 8 on each side, right? This one's a little bit different. It's not 7 and 9. I have 7 and 8, right? Doesn't matter. Okay. So x is the number that we flip, right? So x is either 7 or 8, right? What is the expected value of x, right? So in average, what do you get?
The average is 7 plus 8 divided by 2.
What is it again?
7 plus 8 divided by 2.
Exactly. The average is 7.5, right?
And then my question is going to be, what's the difference between mean and E of X?
Oh, it's the same thing. There's no difference. Mean and expected value of x are two different, basically, phrases for the same thing. Mean of x is the same thing as expected value of x.
According to the formula, it's going to be 1 over the probability.
No, that's a different story, right? So here, if you remember this, the way we solved, so before jumping between two different concepts, here the way we calculated E of x was we used the definition, right? We said that is 7 times 1 divided by 2 plus 8 times 1 divided by 2, right? And that's 7.5, right? We use the definition of the expected value, right? So for the case of geometric distribution, right? So we roll a die x times. That's a very good question, right? I'm happy to ask that because you will see that why the equations are useful, right? We roll a die x times until we get a 6, right? So we roll a die x times until we get a 6. The question is, what is E of x, right? So from the previous slide or from intuition, we know that if we want to roll a die x times until we get a 6, in average, how many times should we roll a die? 6 times, right? That's from intuition, right? But let's use the definition of the expected value to derive that, right? So the answer will be E of x is sigma x f of x, right? That's the definition of the expected value, right? Okay, so that is 1 times f of 1 plus 2 times f of 2 plus dot 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 all the way to infinity, right? Now what is f? F is the probability of success in geometric distribution. So f of x is 1 minus p to the power x minus 1 times p, right? So that means that now in this equation, I have to plug in 1 times f of 1. So f of 1 is basically p, so 1 over 6, right? F of 2 is 2 times f of 2. Now f of 2 is 1 minus p, which is 5 divided by 6 to the power 1 times p, which is 1 divided by 6, plus, now I have to sum infinite numbers, right? It's an infinite sum, right? And there are, techniques in series that, if we have to use, and at the end we get 6, right? So this is the definition of expected value. But to calculate the answer of expected value, I didn't use the definition. I used the equation provided, in the crib sheet or, provided by the geometric distribution, right? So that whenever we see a geometric distribution, we don't have to calculate this infinite sum anymore. That takes a lot of time. Instead, we simply use 1 divided by p. Right? Did I answer your question? Yeah. So there are there are 2 ways to calculate expected value. One way is to plug into this equation, right? We have an equation, that's the definition of the expected value, right? But, if we have a binomial distribution, it's the same story. We can plug in the, probabilities and calculate this sum, but it becomes very difficult, right? You have to add like infinite numbers. In fact, you have to write a code for that, right? Because you can't add infinite numbers with your calculator. Right? Yeah, so that's why we provide these equations. Any questions? All right. So if we have a distribution that is that only takes one value, 8, and the probability of getting 8 is 1, right? So for example, you're flipping a coin, both sides of the coin are 1, right? So in this case, the variance is 0. There's no variation. The other experiment is you're rolling a die, right? And there are 6 sides to the die. 2 sides of the die have 7, 2 sides have 8, and 2 sides have 9, right? So there are only 3 numbers on that die. It's a special die, right? So probability of 7 is 1 divided by 3, and probability all of the other ones is also 1 divided by 3, right? So in this case, again, the average value that we get is 8. Can anybody say how I calculated the variance here? Raise your hand if you know the answer. Why is the variance 8 divided by 12? Where did that come from? Yeah, go ahead.
It's not the uniform distribution.
Exactly, yes. Yeah, and I saw that Anna was looking at the crib sheet. That's also correct. Yeah, it's the uniform distribution, right? So I don't remember the equation either, but it was like something divided by b minus a plus 2 plus 1 to the power 2, something like that, right? Do you see the equation? Was it 8 divided by b minus a plus 1 to the power 2? Yeah? Oh, okay. So I use this equation, right? This is a uniform distribution, right? Again, same story for the variance, right? We could plug into the equation, right? Remember the equation for the variance? We could plug that in, right? So basically, the computation equation for variance was sigma x squared f of x minus mean to the power 2. So in this case, we calculated the mean already. That's 8 to the power 2, right? So we can calculate these, and f of x is always 1 divided by 3, right? So if we plug in and calculate this basically sum, and there's not that many terms. It's only, x is only from 7 to 9, right? So there's only 3 terms. It's not difficult. So if you calculate that, you get the same answer, 8 divided by 12. So, and the third distribution is, another example where, can I get rid of, there you go. So the third example is where we have f3 of x down here, and here, x varies from 5 to 11, right? So we see that, so what is interesting is that in the first experiment, variance is 0. In the second one, variance is a bit bigger. And in the third one, the variance is the largest among these 3 experiments, right? So second case was 8 divided by 12. Here we have 48 divided by 12, right? So you see that as the spread of the outcomes gets larger and larger, the variance also gets larger and larger, right? So that's the intuition behind variance. It means like how much variation you can expect. Any questions? Okay. So far we saw the 2 distributions. In binomial, we have a fixed number of trials n, and we want to have x successes, right? In the geometric distribution, we are doing the experiment until we see the first success. Once we see the first success, we stop, right? So we don't know beforehand how many times we are doing the experiment, right? And we basically saw the equation, right? Now the third distribution, the third interesting one, in fact, it's the fourth one because the first one was the uniform, right? But that's very simple, right? So the third not interesting because uniform is also interesting. So the third probably complex distribution is negative binomial distribution, right? So here, again, I don't know how many times I'm repeating the experiment. So I'm repeating the experiment x times. But instead of 1 success in geometric, I want first r successes, right? So like in the experiment of rolling a die, right? If the success was getting a 6, here I want to roll a die until I get 6 twice, for example, or until I get a 6 5 times, right? Okay, and this is the equation for the negative binomial, right? The proof is really easy, right? I encourage you to find out why. This equation sounds complex, right? But the idea, I basically help you out for the proof. The proof is going to be as follows. You say that you're doing the experiment x times, right? And by the way, they are independent. I don't know if I said it here. Yeah, I didn't say, but they are independent, right? So the trials are independent from each other. So I'm doing x minus 1 and x, right? So I'm doing x trials, right? And I want to have r successes, right? So that means that, let's say I want to roll a die until I get 2 6s, right? So it means that the x time that I roll a die for sure is a time that I get a 6 because I immediately stop after, I get 2 6s, right? So in this case, the x time is a success, right? So the last time is a success. And among these x minus 1 cases, I have r minus 1 successes. Right? And you multiply the 2 probabilities by each other, right? So this is binomial. The proof is not part of this course, but I really encourage you to try to think why this equation is correct, right? This is in fact very similar to the binomial equation. It's because these r minus 1 trials at the beginning are binomial. Okay, so for the case of the mean, the equation for the mean is r divided by p. Again, this is very, very intuitive. Let me tell you why. So we roll a die x times until we get 3 times 6, right? I don't mean 3 times 6. I mean like we get 3 6s, right? So our goal, let's say you're playing a game and you win the game if you roll, 6 3 times. Maybe I should write till we, in my English, the sentence wasn't good, so we roll 6 3 times, right? So our goal is to repeat the experiment until we get 3 6s, right? So we know that the probability of success in this experiment is 1 divided by 6, right? So the expected value of x, how many times we have to roll according to the equation, is 3 times 1 divided by 6. Sorry, 3 times 1 divided by 1 divided by 6, and that's 18. So again, this must be intuitive to you, right? You probably don't even need the equation. If you want to roll 6 3 times, you know that in average we need 18 rolls, right? It's the number of successes that you want are times 1 divided by p. Any questions? And again, you see, like this is the easy solution, right? The difficult solution would be to use the equation for expected value. Remember, we have the equation for the expected value, right? So we can say, so this is the easy solution. We get 18. So the hard solution. So hard solution, it gives you the identical answer, but it's very hard actually to get the final answer. This is going to be the hard solution. So E of x is going to be sigma x f of x. That's going to be probably, so what was this? Oh, that's actually a hard question. So I want to basically, I'm rolling the die x times until I get 6, right? 3 times. So what is the minimum value for x here? If you know the answer, raise your hand. So like, what is the range for my x here in this previous example? Again, I want to find the mean value of x. Here I want to use the definition, right? Let's say I'm very hardcore. I refuse to use any equation. I want to use the definition to calculate the answer, right? What is the range for x? What is the minimum value? Let's talk about the number that I have to write down here. X is equal to, raise your hand if you know the answer. It's a very good question. Say your name again. Oliver. Yeah, go ahead. Yeah, exactly. Yeah, but my question was simpler. But yeah, 3 to infinity, right? Because the minimum number that x can take is 3, right? Because I want to have 3 successes, right? It's impossible to roll less than 3 times and get a 6, right? And f of x comes from this equation, right? So I have f of x, and I have the range for my x. I just need to plug in and it's an infinite sum. So there's no way to calculate this by hand. You have to plug it into a computer. So you have to write a code for it, right? And at the end, the number that you get is the same number, 18, right? So that's why, these equations are useful, right? They are a better way to calculate, expected value, variance, and so forth. Any questions? All right, so let's look at another example. Let's do this one in the next class because these are two different examples with two different solutions. So see you guys on Wednesday. Remember, there's a quiz tomorrow.